Students, Namaskar. We have studied two theorems about symmetric and skew symmetric matrices. The third theorem now we are going to study here, and the statement of the theorem is any square matrix can be expressed as sum of a symmetric and a skew symmetric matrix. So here we go. Theorem number third, and the statement of the theorem is any square matrix can be expressed as a sum of a symmetric and a skew symmetric matrix. So any square matrix can be expressed as a sum of symmetric and a skew symmetric matrix. Students, if I talk about the proof from, or you can say the previous theorem, from the previous theorem, you can say from the previous theorem we know that for a square matrix A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. Dear students, from the previous theorem we know that for a square matrix A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. Now see, A can be written as, if this is so, if A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix, that implies that half of A plus A dash is symmetric matrix and half of A minus A dash is a skew symmetric matrix. Dear students, if we multiply a square matrix by a scalar, it does not change from symmetric to any other matrix or skew symmetric to any other matrix. It will remain, if we multiply a symmetric matrix by a scalar, then it will remain symmetric only, and if we multiply a skew symmetric matrix by a scalar, it will remain skew symmetric only. So when we multiply A plus A dash by half, then A plus A dash was a symmetric matrix, it will remain symmetric only, and if we multiply A minus A dash by a scalar half, it will obviously remain skew symmetric matrix only. So now we know that A can be written as half of A plus A dash plus half of A minus A dash. If you simplify this, half of A plus half of A dash plus half of A minus half of A dash. So half of A dash plus half of A dash and minus half of A dash will be cancelled, and half of A plus half of A is equal to A, and A is equal to A. So I can say A can be expressed of this particular form. If you simplify this, you will get it as A only. So when A can be expressed as sum of these two matrices, then we can say that implies that A is equal to a symmetric matrix and plus what is this? This is a skew symmetric matrix. So here I can write a skew symmetric matrix. So students, we have expressed A as this plus this. This is actually a symmetric matrix and this is a skew symmetric matrix, and that is how A has been expressed as a sum of symmetric and a skew symmetric matrix. So that was only the statement of our theorem. The statement of the theorem is any square matrix A can be expressed as a sum of a symmetric and a skew symmetric matrix. So I hope you have understood it. So the next theorem, theorem number 4, we are going to study, students, is for a square matrix A, AAT, or you can say AA dash and A dash A are symmetric matrices. Here I am writing the statement of theorem number 4. For a square matrix A, for a square matrix A, A dash and A dash A are symmetric matrices. So students, the proof for this particular theorem is, what we have to prove? We have to prove for a square matrix A dash, A times A dash is a symmetric matrix, also A dash times A is also a symmetric matrix. So here we go. For a square matrix A, let P is equal to A dash. The first matrix which we have proved symmetric, I have supposed as P. Now we have to prove P is a symmetric matrix, so we will find the transpose of P. So transpose of P is P dash, and that is equal to A dash whole dash. That implies that P dash is equal to, students, I am writing A dash whole dash times A dash. How it has been written? As we know that AB whole dash is equal to B dash times A dash, means the transpose of product of A and B is equal to the transpose of B times transpose of A. This is one of the properties we studied about transpose of matrices. So I hope you remember this, and using this particular property I have written that the transpose of A times A dash is equal to transpose of A dash times transpose of A. Now this can be written as P dash is equal to, means the transpose of P is equal to A double dash is equal to A only, and this is A dash. As we know how it has been written, what property has been used here? A double dash is equal to A only. This is also one of the properties we have used here. And now this implies that P dash is equal to, what is this? This is P only. So P dash is equal to P, implies that P is a symmetric matrix. P is a symmetric matrix. And when P is a symmetric matrix, students, we can say that A times A dash is a symmetric matrix, and that is what we have to prove. I hope you have understood it. Let us talk about the next one, and similarly you can do the next also. We will suppose for a square matrix A, we will suppose Q is equal to A dash times A dash times A, and we have to prove this as a symmetric matrix. So in order to prove Q as a symmetric matrix, we'll find the transpose of Q, and transpose of Q is equal to A dash times A's transpose. And now Q dash is equal to 8 days times 8 days whole days. What property has been used here from this to this? The same property, this one. Okay, and now q days is equal to 8 days times what is a double days? A only, can be written as q days is equal to what is this? Q. And now we can say, since for a matrix q, q days is equal to q, therefore q is a symmetric matrix. So that implies that q is a symmetric matrix. Symmetric matrix. And when q is a symmetric matrix, you can say 8 days times A is a symmetric matrix, and that is what we have to prove. Hence proved. So we have proved for a square matrix A times A days and A days times A are symmetric matrices. I hope you have understood. Thank you very much.